This is super scientist Johannes Kepler. Who was Johannes Kepler? Well, he was a master mathematician, and he also had an epic stash and a beard combo, as we will see. Pretty sweet. In all his pictures, he looks pretty freaking awesome. He's like rocking the epic stash, epic beard. He looks like a cool pirate or something. I don't know. Pretty cool. Kepler here was very instrumental, just like our boy Galileo, in laying foundations for astronomy that we'll discover. And his one thing is three different things, which we will briefly talk about. He was born 381 years before, for all you people who know him, ages me a little bit, but that's okay. Another German dude, David Hasselhoff. So anybody knows David Hasselhoff from Knight Rider and Baywatch? Yeah, that fun stuff. Anyway, another German dude. So Johannes Kepler here was German, so I want to throw a German guy there. Kepler was also famous for, he wrote a sci-fi story. I don't know if the story was that famous really when he wrote it, but it's still known today. It's called Somnium. It's the kind of technically known as the first sci-fi story. And it's a story about this guy actually takes this trip to the moon, this like witch or something, describes this journey that he can take to the moon. And lo and behold, 400-ish years later, we landed on the moon. So pretty cool. So his big thing that he did was he discovered, if we can guess, 3 laws of, that's right, planetary motion. Exclamation point. Discovered 3 laws of planetary motion. His big boy mathematics, his big boy observations, he discovered that the planets actually have these laws, if you will, or they follow this mathematical formulas that he devised and he figured out. He was a master mathematician after all, and he had a sweet epic pirate beard. What are these 3 laws? Let's dive in. Okay, so law number 1 with our boy Kepler here. He discovered that planets orbit in ellipses with the sun as a focus. What does that mean? Previously, a lot of smart people had thought the planets went in like, here's the sun, and then everyone and their mother and their brother thought the planets orbit in circles. Not the best circle, but just go with me here. So we have planets going in circles here. We have all their planets going in circles, just like this, all the way around, doing their best circle stuff. And we got planets going in circles. Well, Kepler actually found that they're actually not orbiting in circles, but something called an ellipse. So if we have the sun here in the middle, an ellipse is a flattened circle. So we have our orbit of a planet going around. Let's say this is Earth here. We're going around. And we got the sun over here. And an ellipse is a flattened circle. It's almost like when you see the pizza dough, someone throwing pizza dough around, you see like it's all very flattened and it's like, oh, that's this cool flat thing. That is what an ellipse is, and that's what Kepler actually discovered. He used his big math and his big brains to discover that. A focus is simply a point along the ellipse, and an ellipse actually has 2 focuses, so that basically would mean another focus would be right here, an empty point in space. And basically, also I learned this, but a circle is an ellipse with a focus at one point. Both its foci are at one point. Kind of crazy. Didn't know that. But anyway, so it has this 2, is it foci or focus? Whatever. Anyway, foci, focus, whatever. Whichever one's the plural and singular, I forget actually. But anyway, so we got our ellipse here, and he discovered that they're actually ellipses. This was a big radical change and departure in discovering that they actually orbit in an ellipse. Okay, on to number 2, Mr. Kepler's law number 2 of planetary motion. Planets sweep out equal areas in equal times in their orbits. What does that mean? I don't know. Just kidding, I know. Okay, so what this means actually is equal times Equal areas and equal times. I looked online, it was a little confusing at first, but if you actually think about it, that's the sun stuff. Now, actually, there's a consequence as well. So basically, these are these triangles. You draw a line, circle around. We gotta do this here. Third is around. You draw a line right here. We need to cut a line. Let's see, want to see how far it goes. And that's another here. I think this is the triangle. These triangles are that's but in here, this is an area of this triangle. Let's slice this. Well, when there's a closer to the sun, you'll see this sweeps out an area here, and let's say this whole path for the Earth takes about a month. So that area will take about a month for the Earth to cross. Well, turns out, at any point that you go on the ellipse, let's go here. Well, guess what? That's pretty crazy. This is true of the ellipse and this recording. This is true of all the times that this path, that Earth comes around here. This section, this area, this would take a month as well. Month and a month. So we have here that our boy Kepler actually devised a method. He actually saw that it doesn't matter what lines you draw on this ellipse, like this flattened circle, it's always going to be the same area, whatever kind of triangle you'd want to make out of it, no matter if it's a long skinny triangle or a short chunky one. It's always going to be the same area. And furthermore, it's going to be the same time. So we have times and area. So it's always the equals time and area. So no matter where you go, no matter how flat it is, it's always the same time, same area. That's going to take a month to get across, and that's going to take a month to get across. Why is that? A consequence of this law that he discovered, our German pirate, is that basically this area here, this is closer to the sun and it feels the gravitational effect of our big boy sun, and so it's fleeing a lot faster. And so even though this distance well, it may look a little bit longer technically than this, because it's closer to the sun at this point, it actually moves a lot faster, and it takes a month to cross this distance, which is a little bit longer. But then it takes slower over here because it's further away from the sun. The gravity of the sun is actually affecting us a lot less out over here. So in the course of an ellipse, as we're going around, the sun is slightly off center. It's not going to be right in the middle. So we have the sun here burning around. As we're going around, the closer we are over here, we actually move a lot faster. So pretty cool. That's a consequence of his theory. And we're over here on the further part of the ellipse. We actually move a little tiny bit slower, swinging around over here versus over here. Pretty crazy. That is law number 2. On to number 3. Okay, on to big boy number 3. Law number 3 of planetary motion, according to our German pirate. He basically compares the orbits of different planets, and he finds a relationship, an amazing, crazy relationship. He finds that the farther a planet from the sun, the longer it takes to orbit. Now, we can think about that intuitively, right? You think about like, oh yeah, like Jupiter's way out there, and Saturn, Uranus, Neptune, they're way out there. They take much longer to go around the sun. Their years are like hundreds and way longer than our year. Mercury, for instance, takes 88 days to orbit the sun, much closer. So we're further out, we take 365 days to orbit the sun. So we take longer to go around. It's also worded in a different way, very mathematical, precise way, and I'm going to explain that relationship a little bit here. So he finds that the square the time it takes a planet to orbit the sun. So if you square the time, that is directly proportional to the cube of the length of the big radius of an ellipse. What does that mean? Well, it's confusing. It's math language. I like to say this in basic English language: the further a planet from the sun, the longer it takes to orbit. But if you want to do the fun mathematical thing, the time cube squared the time squared over the length of the base of the big radius cube. So what's really weird about ellipses, if you guys know radiuses of circles, there's only one radius on a circle. It's half the diameter of the circle. Well, an ellipse has 2 radiuses because, remember, it's a flattened circle. It's a weird shape. So because it's flattened, it actually has a radius here and a radius here. Oh, that's weird. But our boy Kepler here is talking about this radius, the major axis, called the semi-major. If you cube that, so basically if it's going around the sun, let's say the sun's right here on the path of a planet, if you cube that, and you square the time it takes on the orbit, this relationship is always the same for every planet no matter what. As a consequence, the further a planet or the farther a planet from the sun, the longer it takes to orbit because of this relationship. Because when you square the time, and you cube the radius, it's going to give you the distance that it is, or it's going to give you how far it is from the sun. And you come to find out that this weird mathematical relationship exists for every planet in our solar system. It even exists for the moons as well, which is crazy. A lot of moons follow this proportion exactly, almost right to the T, and it's pretty crazy. So I like to think of it just like this in my big boy brain, just the farther a planet from the sun, the longer it takes to orbit. So just think of Pluto with its super long years, whereas Mercury has a year of 88 days because it's a lot closer. So it's like that. So just think about that, shorter years almost, if you will, as a fun, less mathematical approach to that law, just for us common folk, us non-bearded pirate folk that aren't German, okay? But anyway, ellipses are pretty cool. So that's our boy Kepler with his amazing 3 laws of planetary motion. So Kepler's laws here really laid the foundation for Isaac Newton, that's right, Fig Newton, and gravity, the discovery of gravity, and all Newton's work that he did later on, and his Principia and all this amazing math that he did, his mega genius brain, his calculus, all this stuff. Kepler here really lays the foundation for the discovery of gravity. Unknowns to him, he was just figuring out the orbits of the planets. He was just interested in the math on that. So he lays the foundation for Newton. He improved the heliocentric model, which I talked about. Hyper accurate measurements of the planets and their orbits down to, I don't think he got it precisely right, but for the first time he understood the mathematical underpinnings of how they're orbiting, and he laid that foundation for astronomers that we still use to this day. Amazing work there. This was back in the 1600s he did this. I believe it was around the teens, almost 1620 that he figured this out. Pretty amazing stuff. So no more circles, no more epicycles, gone are the day of Aristotle and Copernicus, no more of that stuff. So our master mathematician here and German pirate Johannes Kepler, thank you for giving us a greater understanding of how the planets are moving around, including our planet. Thank you, Mr. Kepler. And thank you all for watching. Please like, comment, and hit that sub sandwich button. See you next time.